This is being conducted as part of a knowledge transfer partnership with Northumbria University and Space Architects, so it's being integrated into the practice as the research is conducted. So worldwide, the construction industry is responsible for 39% of carbon emissions, with 28% being from operational carbon and 11% being from embodied carbon. The construction industry has a vital part to play in addressing the climate emergency. Within the UK, operational carbon is more regulated than embodied carbon, with approved document L, which regulates operational carbon emissions. There are currently no government policies within the UK that require the assessment or control of embodied carbon. Voluntary targets have been set in the UK by construction professionals for the reduction of embodied and operational carbon. Architects have a key role to play in the reduction. Within the design process, the early stage design decisions that are made cannot be automatically analysed for their impact. Good early stage design decisions can reduce the whole life carbon of a project. The majority of architectural practices currently rely on in-house knowledge to make design decisions regarding whole life carbon due to lack of access to specialist knowledge or simple design tools. In the earliest design stages, architects define the whole life carbon of a building, often unknowingly, over its whole life cycle due to the lack of availability of analytical tools. Current literature shows that good early stage design decisions can reduce the whole life carbon of a project. The results of the questionnaire conducted within practice covered a wide spread of people across various stages of their careers. The majority of them were architects or somewhere in that field. The most common response for lack of integration of embodied carbon analysis is the lack of knowledge and time. Alongside this, there were comments about the lack of suitable software in order to automate the process. It was discussed that the more automated the process of analysis, the more likely it will be to be integrated into the design process. In terms of tools that are currently used in practice, the practice that I focused on use Revit from a very early design stage, so they use it from concept stage or RIBA stage 2 and 3. Key decisions regarding embodied carbon are currently made at RIBA stage 2 and 3. So therefore, analysis needs to be considered from this stage and earlier, not from stage 4, as the questionnaire showed. Very limited people within the practice have undertaken a life cycle assessment, showing that the process needs to be more ingrained in the workflow and more accessible. So the majority of people have never conducted one, and then very limited people have had it outsourced. So these are a series of voluntary targets that have been set by UK construction professionals, which go in line with BSEN 15978. In order to accurately measure the embodied carbon of a project, a level of materiality and detail needs to be within the design. To be able to reach the benchmark set, decisions need to be analysed and made prior to material decisions. Right. Certain decisions are made within RIBA stage 2 or concept design stage that impact the whole life carbon of a project. These are such as site location, form factor, which is the ratio of gross internal area to heat loss area. So not only does that impact the operational carbon in terms of heat loss area, but it impacts the embodied carbon, with the lower the form factor being, the simpler the structure. It's been discussed that the building design process doesn't have the tools to analyse and consider whole life carbon in the early stages of design. The most fundamental decisions which will affect the whole life carbon of a building are conducted at this early stage. Whole life carbon isn't limited just to material selection, but it's widely discussed that all of these factors can impact it and reduce the embodied and operational carbon. Considering all of these impacts, it's been shown that it's possible to reduce a design's environmental impact by around 40%. So the typical building frame, for example, could have 40 to 60% less embodied carbon if a simple structural grid was chosen over a complex frame. So these good early stage design decisions, such as form and structural grid, will focus on the major embodied carbon hotspots. providing reductions. Having design analysis from RIBA Stage 2 will assist in the reduction of whole life carbon before material selection even takes place. So this is an example of the current workflow and the proposed workflow. So currently, life cycle analysis is conducted probably from RIBA Stage 4 due to the level of development. So analysis has confirmed that there is a gap in whole life carbon design and analysis during the concept design stage or RIBA Stage 2. The tools currently available can analyse projects with a high level of development, and the tools require a high skill level and are time consuming to use. Creating an IT-based tool that's able to be utilised at an early concept design stage where we have the biggest impact, where we have the ability to have the biggest impact on the whole life carbon is necessary. After reviewing relevant literature, it's apparent that it's not possible to accurately undertake life cycle analysis at early stages of design. The literature did provide an insight into the fact that early stage design decisions can have a large impact. These early stage decisions need to be analysed, and it needs to be done in a way that it can be integrated into architectural practice so that it can be used. This will in turn provide guidance to the designer that the decisions that they're making in their early design stage are setting the project on the right trajectory to reduce the whole life carbon. As the previous survey stated, key decisions are made at RIBA Stage 2 and 3, which is where we'll be focusing the tool. So the tool will be developed to analyse these early stage decisions, providing the designer with feedback about the decisions that they make. With the lack of detail at early stages, such as the lack of materiality and lack of detailed design, the things that will be analysed will include form factor, window to wall ratio, structural grid and orientation, just to ensure that the project is being set on the right trajectory. In line with the tool, a series of benchmarks need to be developed, analysing these design decisions that are being made, just so that we can ensure that the correct decisions are being made. Following the feedback that we got within practice, this tool will have to be automated and take information from the model, which is primarily going to be in Revit. And then it will provide the designer with a graphical representation of any carbon hotspots and room for improvement. So because it will be utilised in architectural practice, the usability of it is very important, so it needs to be very graphical and easy to use so that it can be integrated into the current workflow. This research shows that there is need for future tools and gives the foundation for a future tool to be developed. The analytical process conducted within architectural practice did show the need for a design-based tool that utilises IT tools that are integrated into the design and construction process. To summarise, it is apparent that there is a gap in early stage analysis. Following this initial research, a tool will be developed that can be utilised from the early stages. With it being a Revit-based tool, this should hopefully reduce the learning curve of it being implemented into practice, so it should be an easy to implement tool with little to adopt. Then this should be able to be undertaken before life cycle analysis is conducted at stage 4. Yeah. So this research is being developed as part of a 2-year project with the Knowledge Transfer Partnership funded by Innovate UK, and I think this is 1 year through, so hopefully we'll have the tool developed soon. Yeah. Any questions?